Hello everyone, my name is Henrik Nortamo. I work as an application specialist at CSC, where I maintain the computing environment in our supercomputers. Within the PerMedCoE project, I mainly provide HPC expertise. Now, in this short 10-minute talk, I will be going over what exactly a PerMedCoE building block is, what the interface looks like, and how we use containers in the PerMedCoE building blocks. Now, this project is still early in development, so we really appreciate any feedback you have, especially if you have any wishes or feature requests for the building blocks, which would make them more interesting or easier to use. And then if you already have some criticism of things which will not work or will probably be useless or something alike. So please contact us or let us know if you have any kind of feedback to give. Now, all the code and all the things I will be referencing during this presentation will be available once published on our GitHub. So just GitHub and then PerMedCoE. So without further ado, let's get started. Now, a building block, as the name would imply, is basically the things you use to construct your workflow or simulations pipeline. So you would have your data, and then you pick a bunch of building blocks, let your data go through all the building blocks, and then you get some interesting results or science at the end. So more technically speaking, it's the smallest schedulable unit of the work, which you would then compose a pipeline from. Now, there are three main design principles for the building blocks. One is to unify the application interfaces. So a lot of applications for personalized medicine have different ways of doing basically the exact same thing. How much memory do you want? Where are the output files? Where is the temporary directory? How many processes to launch, etc. And instead of trying to unify at an application level, so going around and telling 20 different developers that, hey, can you actually let the user select things this way and not that way, it's just easier to wrap around them and then translate. And this is basically what the building blocks do. The second point is simplifying the usage, both when actually installing the applications and then when executing them. So the idea is there to hide as much complexity and configuration as we can. And here really putting an emphasizing on enabling non-technical end users to still perform these kind of more heavy-duty analysis workflows or personalized medicine simulations without being developers or HPC experts themselves. And the third point is this equivalence that one building block equals one action. So if you can't explain what the building block does in one sentence, i.e. simulate this cell or transform this data according to this, then it's too complicated. So it's basically one building block is one simple action. So on a technical level, a building block is basically just a thin wrapper around a container. And for those who are not familiar, a container is basically a way to package software in a way that it contains all the necessary dependencies and things needed to run. So you can then basically run it anywhere, at least, let's say, between Linux systems. So your same software can run on Ubuntu and CentOS and GNOME and whatever. The wrapper themselves are implemented using Python, and they are invocable directly from the command line, like a normal binary, or then programmatically using this Python interface. And the idea there then being that the building blocks should be usable out of the box in as many workflow engines, workflow managers, execution engines as possible without any modifications. So that's why there is this binary interface, which is very general, and then this programmatic interface for more complicated things. And the building block completely or almost completely hides the container from the end user. So the end user, basically, if they're invoking individual building blocks or then invoking multiple building blocks through some even higher level workflow manager, they won't know or notice that there's a container running below there, at least if we implement this correctly. As long as there are no issues, it won't be noticeable. And currently, as the first step, we'll be developing building blocks for the PerMedCoE core applications. So Cobra Exa, Selenopt, Mabos, and Physicell, and this will spawn probably a couple of building blocks at least per application. And then after that, we'll start looking at auxiliary building blocks, which are needed for data transformation or some really simple analytic stuff. Then some AI building blocks for simple interference or image recognition. And then hopefully other people outside, just from within the PerMedCoE, will start contributing their own building blocks once they start liking this enough. So in order to entice you to actually start contributing to this, let's look at the interface. So currently the interface is the same for all building blocks. You can see it here on the right. So basically we have an input, which is just a list of files and folders, and an output, which is again a list of files and folders. Then we have these really generic optional arguments, like, okay, give me some debug information, set the log level, where is the temporary directory located, how many processes to launch, do you need GPUs, and how much memory we're going to use. And if the need arises, so we have large enough subcategories, we might split so that you have one type of cell simulation building block, and then one type of AI building block, and one type of numeric data analysis building block. So still giving a bit of granularity there, but still unifying the interfaces between then specific applications. Now we can also pass an optional config file there, which is BB specific. This is probably going to be just a YAML file. And this is so that if there are these needs to tweak specific stuff in a building block, we don't need to clutter this command line interface, but we can just pass it simply through the config file. But then it's also as a file on disk, so it's actually then reproducible. You can use that later. Now, basically what the building block does is it takes all your generic options, and then it contains functionality to just translate this to whatever specific options and formats that the wrapped application actually requires. And also during this, the building block automatically mounts all input files and folders, all output files and folders into the container completely transparently. So again, the user doesn't have to care anything about it. It's not yet published, but it's going to be published fairly soon, hopefully. Is a Python package which enables you to create your own building blocks really easily. Because basically the idea is that after you've managed to containerize your application, the only thing the building block needs is for you to specify the mapping between these generic options and the specific options your application requires. So if your application uses the -f flag for specifying the output file, okay, then you would just specify that, okay, -f will actually just map from the first argument from the generic O flag. Now, just a caution, the interface is subject to change as we're still in early stage in development. So this is not set in stone, might change, but there will be up-to-date documentation once we publish the package itself. So one key component of these building blocks are the containers, which then house the application itself. And here we've chosen Singularity as the container engine. Mainly because it's widely used and available on most HPC platforms, but we do aim to keep the building block container agnostics somewhat in order to support other container engines in the future. Then if people want to, for some Singularity isn't available, or people want to use some specific implementation, for example, Charlie Cloud or Sarus or rootless Docker or something in the future, we would like to enable that use case. Now, the main reason why we are using containers is, for once, you get a reproducible execution. So you know that the code you're running is immutable. You always know how it was installed, and you can even version these containers. So assuming, again, you are doing your data management properly, it's really easy to send all the code and data to someone else and have them basically reproduce the exact same results. We used that version of the PerMedCoE building blocks, and that's the exact data we used, and so on. The other one is this portability and ease of installation. So one, that you install the application inside the container, and then it should be basically work on any of the target systems. And then from the end user's point of view, that, okay, you only need to download the container and then you can run it. You don't need to start installing dependencies, checking how to configure those, configuring them incorrectly, reinstalling them 3 times, and then just giving up. Of course, in a HPC environment, there are caveats to this portability. And this is especially the case when it comes to enabling MPI, so message passing interface, from within the container, and then interacting with the system job schedulers and GPUs. But a part of this project will basically be then to develop utility scripts and tooling to try to make this as portable as possible. Worst case scenario, someone, let's say, a bit more skilled in HPC environments will need to do some initial setup for the building blocks to work out of the box. But then after that, the end user should be able to just come on to some system with the installation done, pull down the building blocks they want to use, and just use them without caring about all the nasty stuff. And these toolings and utility scripts will also be available on the GitHub with instructions. So basically, in summary, the building blocks are the first layer for building HPC-enabled workflow for personalized medicine and really bridging this gap between non-technical end users and HPC experts. So I hope you learned something from this. Thank you very much.